So, as one of the organizers, I feel compelled to set a good example and try to finish within the hour, this being a research talk. So, I've already written up my outline, my collaborators on this work in progress, and my title. So, this is concerned with the following question. ADS-CFT duality holographically maps a higher dimensional bulk into a lower dimensional boundary. And this means that there can be excitations in the boundary that are on top of each other, and therefore should be able to interact strongly with each other, but are actually separated in the bulk until they can't. And from the point of view of the conformal field theory, in the boundary, this is mysterious. It's not obvious. It means a dimension is emerging. And so the point of this work is to understand, from the point of view of the conformal field theory, how one can understand this higher dimensional locality property. So the first part of my talk is about a partial answer, which is also more of a which is very nice, but it's a very nice red herring. So, but we have to talk about it to explain why it's a red herring. So in ADS-CFT duality, we have this holographic mapping between energies and the radial direction of ADS space. And this is just a statement of symmetry, of the fact that there's a warp factor, so that if we have an excitation in the bulk and we move it to different radii, its energy changes due to the warping, and so we get this approximate identification, which is often called holography. And now, there's a sense in which interactions in field theory, or at least in gauge theory, are local in energy. The sort of the easy example is just the renormalization group, where the beta functions at a given scale satisfy an evolution that depends only on the couplings at that scale. So that's an example of the locality. Actually, when I said this at Stanford on Monday, Lenny said, does this mean that a high-energy cosmic ray would pass through my body? Since the high-energy cosmic ray, low-energy body. And remarkably, the answer is yes, if the cosmic ray is appropriately prepared. And this is called color transparency, and I'm not going to explain it because, again, this is a red herring, but it's something we can talk about later. But in fact, yes, there's a real sense in which in gauge theory interactions are local in energy. And therefore, that means they're local in radius. And since we're only talking, I'm focusing here on the ADS factor, so there's only this one emergent direction. And so it seems that this has something to do with why there's this locality. The problem is it's not good enough, because we really only expect this locality in energy to hold at best to order 1. And therefore, the associated locality in radius to hold order 1. And if we think what the ADS metric is, this means that we can understand this locality provided this distance L is greater than RADS. If these are separated by more than an ADS radius, we can understand why they don't interact, maybe because they map into very different energy scales in the field theory. But ADS-CFT duality implies much more, because there is supposed to be a bulk theory, which is an effective local field theory up to the string scale. And the string scale is much smaller. Well, we generally use ADS-CFT duality in a regime where the string scale is much smaller than RADS. And And so what we really need to understand, to fully understand this question, is how it is that the physics can be local on a much, much smaller scale than this energy radius argument gives us.
So here you're talking about basically blue balls or gravity.
That's what I'm thinking about, right.
You can look at D-brain probes or things that go out on the moduli space.
I'm thinking about the things which in the CFT are the simplest observables, which are the endpoint functions of gauge invariant operators. So these would be glue balls, as opposed to motion on the moduli space, which is, that's also interesting. But I'm focused on scattering gauge invariant operators, and therefore things like glue balls. Okay. So this energy argument, elegant as it is, only sort of gives us what I like to call coarse holography. And what we want to understand is we want to understand locality down to down to a much smaller scale, a parametrically smaller scale, the string scale, which I'll call precision holography. So the focus of this talk is on precision holography. How do we see that from the point of view of the CFT? Okay, so now let me show you how one can characterize this in terms of the correlators of the conformal field theory. And so let's consider global ADS space with Lorentzian time. And we can consider a 4-point function where we have a couple operators, a couple local gauge invariant operators in the past and a couple local gauge invariant operators later on. And so we can think about these acting on the vacuum and creating excitations, which come in, interact, and then go back to the boundary and are destroyed. And to probe the locality properties, we can fold these into wave packets so that as they propagate into the interior, they don't spread too much. And it's not hard to do a little bit of analysis, wave analysis, and see that you can in fact make beams basically that have a smaller width than the ADS radius. You can make the width of these beams parametrically smaller than the ADS radius, and so you can do a thought experiment that probes this locality. So what you're doing here is you have a correlator in the gauge theory, 4-point function. Its position as a function of this. This picture is obviously Lorentzian. Later, I'll actually go to Euclidean space times, but it's a function of time and angles or a unit vector on the sphere. But then to make the wave packets, we want to make these beams. We need to also fold these into wave packets. Sorry, I didn't leave enough room there, but that just says that you take this 4-point function, but now you fold the arguments into wave packets that are not too wide, not too narrow. You make them just right, and you can focus these beams. And now, one way to think about the locality is, if you change these wave packets a little bit where they are or what their momentum is, the beams will miss. And this amplitude will rapidly fall. So it's very strongly peaked when these particle beams intersect in the bulk.
Joe?
Yes?
You're calling these beams, but these are finite size or finite width beams on the boundary theory? Or in the bulk, they're actually becoming infinitely wide?
Well, they spread due to the uncertainty principle. But what I'm saying is that you can find, in the limit that we're interested in, where, again, the ADS radius is large compared to physical scales like the string scale, you can choose packets which are small both in angular size and delta t, but still are also narrow enough in momentum space that they don't spread much as you go into the interior.
I was asking about the fact that in the metric there's an r squared in
Yes?
front of sort of the d omega
right.
or something. So any finite d theta is going to end up being arbitrarily big.
Oh, I'm sorry. Right, yes, I'm sorry, yes. So near if you're sitting just inside the boundary here, this beam is infinitely, but in the region where they would interact, you're using the metric in the interior of ADS, and there I'm saying it's smaller than the ADS region. Yeah. Okay, so locality is then the statement that this 4-point function has this mysterious property. So from the point of view of the CFT, changing the wave packet a little bit looks like a small change. There's nothing at all, there's nothing at all from the point of view of the boundary special about changing, well, not nothing, but there's very little special about changing the wave packet a little bit so that in the way I described. But from the point of view of the bulk, it's clear that this is going to lead to a radical change in the answer. And so this is a quantitative statement of what locality means in terms of the 4-point function.
Let me be the one to ask the annoying question. Doesn't one of your colleagues keep writing papers saying that things are very difficult?
Good. So Steve Giddings doesn't believe this, and he has therefore done more than anybody else to develop it and turn it into a useful tool. Which is really a good way to proceed. I mean, you shouldn't believe everything. And in particular, Michael Gary and Joao, so this nicely recast what I just said as the statement that this 4-point function has to have a certain singularity when these 4 points are appropriately aligned. So that's a much more succinct way of saying what one needs. And this statement, this singularity, is certainly not something which is present in general conformal field theories. It doesn't hold. It's not present, for example, in the weakly coupled n=4 gauge theory. It's something that emerges in the strong coupling limit, which is also the limit in which the bulk space-time emerges. Steve also has issues with the exact width of these packets and so on, but actually I don't need to go into this because the only thing that I want you to take away from this part of the talk is the idea that by looking at the 4-point function in the conformal field theory, we can probe this question of locality in the bulk. And in fact, later in the talk, I'll give an even simpler and more pragmatic characterization of locality. By the way, I should emphasize, so this theory is conformally invariant. The 2-point function, the 3-point function, their functional dependence is completely determined by symmetry, and so doesn't carry any dynamical information. The 4-point function is not completely determined by symmetry. You're all familiar with the string world sheet, where after imposing the symmetries, you have a function of basically 1 complex or 2 real cross ratios. And in fact, that turns out to be true in every dimension. Symmetry reduces this to a function of 2 real cross ratios, and that function has a lot of dynamical information, and in particular, it has or doesn't have the singularity that would characterize this local physics in the bulk. Okay, so now let's ask about the current understanding of this precision holography. Has it been tested? So there's a gazillion tests of ADS-CFT duality. Juan's paper has 6,000 citations. And in principle, every one of those papers that uses it is testing it, because if it gets a nonsense result, it would imply that there was something wrong with the duality. So it's passed many...
Those papers weren't written.
Pardon?
Those papers weren't written down.
Thanks to the selection effect here. Have you got some in your drawer? Okay. So there's many. Let me just list some of the broad classes of tests. So many BPS states and amplitudes have been studied. There's the behavior under symmetry breaking and RG flow, which it's very much complementary to the BPS tests because it completely doesn't use the symmetries, seemingly. Namely, if you deform the theory in some way, if you deform the CFT in some way, the response of the bulk is exactly what you'd expect. It confines or breaks chiral symmetry in just the way that you would expect from gauge theory intuition. So, it shows that beyond just these extreme supersymmetric things, duality is capturing something dynamical. There's integrability, this symmetry structure on both sides, where you seem to now be able to connect them smoothly. There's numerical tests, and there's at least a couple different types. There's some on the light cone DLCQ, numerically solving light cone Hamiltonians, and then there's early work on Monte Carlo simulations. And we can even compare with experiment, namely RIC. There's probably more. Again, these are just categories. In each of these categories, there's many things that you could think of. There's probably tests that don't fit any of these categories, but let's ask whether any of them test precision holography. And so this one obviously doesn't, because the 4-point function is not BPS. The 2- and 3-point functions are, but that doesn't get you into the dynamics. Symmetry and RG flow really just uses what I called coarse holography. It uses the mapping between radius and energy, but it doesn't probe it on finer scales than that.
Again, unless you got on the Coulomb branch, say.
Okay, so well. Okay, good. So I don't want to. I actually haven't thought. So the observables that you're talking about, which again are motions on the moduli space. We should think about that. I don't have a quick answer. It's possible that it's been tested. That's a good question. Has it been tested there? We'll see. But that certainly, again, for these observables, the correlations of gauge invariant operators, right. That's a good question. We should think about that, because maybe we already know more than. Integrability. Integrability really just, in its current state of knowledge, it only talks about the 2-point function. It's, with all the progress, it's only the spectrum of operator dimensions so far that one can understand, and not the entire, not things like the 4-point function. So no. Numerical tests are still at a level of crudeness that just gives approximate information about the 2-point function. Actually, comparison with RIC seems like it has some potential, because certainly when we talk about things like jet quenching, we're drawing these very detailed pictures in the bulk and claiming that they are somehow reflected in RIC physics.
That's out another class of so-called observables, post-observables, which are the gluon amplitudes.
The gluon, yes, good. Actually,
there are many tests.
Yes, but the gluon amplitudes, I believe it's correct to say, the way that Alday and Malacina constructed these was to go out a little bit on the Coulomb branch. The strings are stuck to those Coulomb branch D-branes, so they don't propagate in the bulk. They're not. I don't believe those amplitudes address the emergent fifth dimension.
In string theory, they're this case is described by surfaces.
So now, right.
Direct test of strings.
When you say a test, it's a test because it's a test because you can calculate at weak coupling, calculate the strong coupling, get the same form.
The same form, which by the standard of this game is proven. You can prove it's determined. I mean, you can calculate now.
Okay,
it's pretty powerful agreement of a conjecture. And those are other equally well probes of locality. The same way that you're doing with wave packets, you could construct gluon amplitudes and power. I mean, you have to, of course, regulate them. And the string theory gives you a nice way of regulating them.
Okay, this is good. So gluon scattering.
At least you know how to do it in
So here.
string theory.
Okay, so I'm gonna leave these both as exercises for the audience or for graduate students or someone to figure out whether in fact these really do probe this locality property, whether they really do things that from the point of view of the CFT are mysterious in the way that I've described here. I don't think it's obvious, but yeah. Actually, so I seem to be doing well on time. I'll mention another test, which the 3/4, which also came from an audience member. The 3/4 in the black 3-brane entropy. In the bulk, this comes from the detailed form of the Schwarzschild metric. It comes from having having the space-time described in a precise way, and so it would be a consequence of precision holography, but not of coarse holography. Now, that 3/4 hasn't really been tested. It's consistent with Monte Carlo simulations, and it's consistent with RIC, and it's consistent with extrapolations from both ends. But if one could, in fact, verify that 3/4 in a precise way, that would also be a test of precision holography. Okay. So, good. These are interesting open questions. I don't want to say, okay, good. But I still have the question, why do the correlators of local gauge invariant operators have this funny locality property? Why do they have, do we know that they have these singularities that locality requires? So, one talks about, can ADS-CFT be wrong? That is, could it be true? Could it be that it holds, in spite of all of the tests, only in some weak sense and not in the strong form that we all assume? And one possible version of the weak form is that the n equals 4 gauge theory is dual not to string theory in the bulk, but to string theory, something like string theory, but smeared over an ADS radius. So if holography just came from this, just came from the energy radius mapping, then you really could only you could only say that you had the weaker.
More precise as to how you smear.
Well, in fact, I'm going to. Yes, I can, but not yet. Yes, I can. Good. And again, perhaps one can already say that weaker form has been falsified by these. We'll see. But I'm going to try to falsify it or maybe construct it. Good. Okay, so these are the issues, and now the conjecture. So precision holography. This holography at scales below the horizon. So this requires that that again there be this. Well, it's only meaningful if the string scale is much smaller than the ADS scale. Now, the ADS-CFT dictionary says that the dimension of any operator is related to the mass of the corresponding particle state in ADS space. And for Kaluza-Klein states, this mass is of order 1 over R ADS, and so this is order 1 for Kaluza-Klein states. For string states, this is of order R ADS squared over L string squared, which is lambda to the 1/2, which is much greater than 1. So precision holography, that is having a hierarchy between these two scales, implies that most operators get large anomalous dimensions. So the conjecture is that that this actually is both a necessary and sufficient condition. That is, a large gap in the spectrum of anomalous dimensions also implies that the conformal field theory has this higher dimensional locality property. I actually thought that this was folklore, but as I ask around, I find that it's folklore that nobody's ever heard of. So I guess it's one of those things that was batted around a little bit in after Juan's paper, but never rose to the level of folklore.
Well, so one of the things that was batted around was the question of whether the right-hand side depends on supersymmetry or not.
Right. Well,
so I guess we'll see.
Well, I will not use supersymmetry directly. We know that, of course, non-supersymmetric examples have potential pathologies, right. But I'm not going to use supersymmetry directly.
Or what depends on supersymmetry would be the existence of the gap.
Right.
Not that most operators get large dimensions.
Right. Well, there are not there.
Well, you know the stress center is always going to be It's a question of whether the other operators get driven.
I mean, there are large N inheritance principles. If you break supersymmetry, if you break all this by orbital folding, you keep the gap because of large N inheritance.
Yeah.
Then there's a question: are there other pathologies that come in?
But it would be the protection of certain operators that is a consequence of supersymmetry, not the large.
Oh wait, the stress center is always going to have dimension 4.
There's symmetry, so there could be global symmetry.
But not necessarily.
In any theory.
Not necessarily supersymmetry, right?
Some symmetry. Supersymmetry gives you a lot more than you would have to just by conserved currents.
Yes.
So the statement is that if you have this large gap in the spectrum of operator dimensions, then you will have a classical bulk dual.
Then you have a classical bulk dual, right? And I should say, I mean, so large gap is not real precise. I don't know what the most precise form of the conjecture would be. Today we'll only talk about testing it in the simplest possible special case. But a plausible conjecture would be that most means all single trace operators of spin greater than 2. The reason for that conjecture is that a single trace operator of spin greater than 2 would be dual to a particle with spin greater than 2. And we don't know of any effective field theories with parametrically light fields of spin greater than 2. So this seems to be a necessary condition, and it's also a plausible sufficient condition for this to hold. Anyway, we're not going to test it in this level of generality, but we're going to test. Well, good. Okay.
So, but doesn't integrability, in some sense, potentially it can shed light on this issue?
If you can extend it to the 4-point function, but
No, but just the notion of operators having large anomalous dimensions.
Yeah. Okay. Good. Thank you. So good. So if this conjecture is true, then, thank you, it replaces this mysterious property of the 4-point function with a much less mysterious property of the dimensions, something which has an obvious intuitive origin in terms of strong coupling, giving large dimensions to anything not protected, and something which indeed can be tested in many ways. So it takes it from something mysterious to something which is more intuitive, more testable.
One of the unsaid assumptions you're starting with any local conformal field theory or any local quantum field theory.
So
with this property,
it's a conformal field theory, and when I said, in order to make the statement, I have to use the word single trace because there are certainly multiple trace operators of high spin of low dimension, and so it also has a 1/n expansion.
But in order to use the word trace, you have to start with a matrix model.
Or simply with a limit where where a limit which satisfies the usual large n, without knowing the details, just a limit in which large n factorization holds, which means that I can separate one particle states from many particle states.
Because I'm just thinking of counterexamples here.
Yeah.
Which, for example, vector model would be a counterexample to this. I mean, at least it would be an example where so far everything you've said holds, but I don't know when you will walk on. Construct one.
No, it's not true, because there are large N vector models. This high spin operator does not get a large anomalous dimension.
Oh, I see.
Yeah.
It has to be this big.
Yeah.
You have to specify more than large to that you are.
But they're right. So to make this statement requires having a, something like 1 over n that enables you to distinguish single particle and multi-particle states. To define large, it requires having something like a TUF parameter that can be varied parametrically. In duals where the bulk is M theory, these are the same thing. You can't vary. You only have 1 over n, and you don't vary them independently, but together. Yeah.
Are you going to make this link in the rest of your talk? Are you going to discuss why this connection the connection between the conjecture and precision holography in the form of the 4-point function?
Yeah. So that's the conjecture, and the second half of the talk is investigating the conjecture, and either showing that it's true, or finding a counterexample. And a counterexample would be interesting because it would be a potential answer to this question, what do we mean by a smeared version of string theory? What would be something that has, this seeming hierarchy of masses without having locality? Okay, so now we're sort of just doing abstract conformal field theory. And the only additional information then is a gap in the dimensions. So a parametrically large gap in the dimensions, and also a 1 over n expansion. So what are the constraints? So there's the operator product expansion. O sub naught is going to be a scalar operator of low dimension, so one of the ones that doesn't get a large dimension. So the operator product expansion says that this is equal to a sum over all operators, schematically x to the dimension of the operator appearing minus twice the dimension of O times, again, some complete basis of operators. Now, we're always going to be using the operator product expansion within the regime where it converges. And what this means is that if you look at you will always have some number less than 1. It might actually be a combination of x and some matrix element. We're always going to have some number less than 1 raised to the power of the dimensions of the operators that appear in the sum. Number less than 1 is being raised to a parametrically large dimension. And so I want to think about the limiting theory in which the operators that get large anomalous dimensions don't appear. And so what I have is a closed operator product algebra just of the low dimension operators. Okay. The second constraint we have is crossing. So the 4-point function is the thing we're interested in. By using the operator product once and twice, we can reduce that to a 2-point function, which is just normalized by definition. And so the 4-point function is just the sums of the squares of the OPE coefficients. And we can do this in more than one way with overlapping radii of convergence. And so these OPE coefficients have to satisfy that. What else is there? There's conformal invariance. Now, modular invariance. Modular invariance we don't have and we don't need. Why not? Well, so first of all, why don't we need it? Because modular invariance relates the low dimension states to the high dimension states. For the purposes of the present discussion, I'm interested in sort of the closed theory of just the low dimension operators. Modular invariance would take us outside of that. But also, if we're thinking about the n equals 4 theory, it's not clear what modular invariance is, because the local operators are dual to the gauge theory on, say, S1 cross S3. And unlike S1 cross S1, which is what we have in 1 + 1 dimensions, it's not clear what modular invariance means. Obviously, we can interchange two S1s, but it's not clear how we would interchange this time circle with one of the spatial circles in the S3. It seems to me there should be some notion like that here, because modular, it just seems, for one thing, modular invariance, it's necessary for thinking about the black hole states. It feels as though morally there should be some way to get some constraint like modular invariance in higher dimensions, but I don't know what it is.
Your closed theory will still have an infinite number of operators doing all the KK modes, or it's really a finite set?
So in the n equals 4 theory, it would have all of those. It would so most means an infinite number, but a smaller infinite number than the ones that are massive.
Yeah. And there's no assumption then on how the string state spectrum grows, so that you can really ignore it.
Well, that assumption is the OPE is just what you get by inserting a complete set of states on the world sheet, and which converges by general principles. And so that's something which already you know. Yeah. There might be some assumption I'm making about the uniformity of the limits or something, but
Is there a reason to be in 4 boundary dimensions instead of 2?
Well, only because only because we'd like to understand this in generality and not with the special extra machinery that comes in 1 + 1. Yeah. But yeah. Okay, so those are the constraints. Okay, now the toy model. So the toy model is going to be. So what's this? Just to see if one can get any mileage at all from these assumptions and ingredients. You'd want to start with the simplest possible case. So the simplest possible case would be that the only low dimension operator is the only single trace low dimension operator is the energy momentum tensor, which would correspond to a bulk theory that has only a graviton. Now, this actually sounds like closely parallel to what's being done in 2 + 1 dimensions. So I should emphasize that our concerns are orthogonal to what's done there. So there, the main interest is on modular invariance in the spectrum of black hole states, which I've just told you we aren't interested in. On the other hand, there you have so much conformal symmetry that the things become trivial. There are no propagating modes of the graviton, so I can't even do my thought experiment. So I'm interested in something which is in some. So again, this is orthogonal. The non-trivial issues are different here than there, but they're both in this general theme of how far can we go with conformal field theory. So this is the simplest possible case, but I want to consider something simpler. So instead of having the energy momentum tensor is the only operator, we're going to have just a single scalar operator as the only operator. Now,
one second. Hey, local field theory has the energy momentum.
Yes, so this is not even a conformal field theory. Nevertheless, when you sort of start doing ADS CFT, you often start warming up with a model that just has a scalar field in bulk, not a graviton. And today, that's all I'm going to do. And I'll tell you what would be involved in going to this case. But I'll tell you that morally, the steps and the constraints in the two cases are entirely parallel. The only difference is that we don't have as many indices. So in going from this theory to this thing that's not even a conformal field theory, we're not we're not radically changing anything. The nature of the constraints and the form will be the same, and so the strategy for solving them will be the same. Yeah.
I thought conformal theory is a field theory.
It's a field theory that doesn't have a Hamiltonian. That is, there's no operator within the theory that takes you. It has correlation functions. The correlation functions satisfy conformal invariance crossing OPE, but it doesn't have a Hamiltonian. There's no operator within the theory that takes you from time t to t plus dt.
Or translation.
Pardon?
Or translation.
Or translations, right.
That's not a correlation.
Right. A bunch of correlation functions that satisfy a bunch of axioms. It's a gerb. Is that right, Dave? Dave says it's a
I guess the modern version is swine gerb.
Okay. Anyway. So, and again, well, I'll talk once we understand this case, we'll talk about what will be involved in going to this case. So, okay, so what I want to do now is, oh wow, I'm already on my last item. So what I want to do now is I want to take the constraints, take the model, and combine them. And so I'm going to write down the resulting relations. So conformal invariant. So we got the 4-point function, and life is simpler when you're Euclidean. So we have the Euclidean 4-point function. We'll talk about getting back to Lorentzian in a second. And we can use conformal invariance to move all of the vertex operators into a single plane. So I need only consider O0 of 0, O0 of z, z and z bar. It's not a holomorphic operator. O0 of 1, the usual thing that we do. Looks like string world sheet, but again, I can always use conformal symmetry to put myself in the plane. And this is equal to using this trick of using the OPE twice to okay. So using the OPE twice, I can write this as a sum over intermediate operators. The C's here, let's see, the G's, I guess the C's are the squares of operator product coefficients. I've also used conformal invariance to its maximal extent here by partly doing the sum over states. That is, I only need to sum explicitly over primary operators. I'll tell you what, I'll list these in a second. The secondary operators, those obtained by total derivatives acting on things, can be summed explicitly due to conformal symmetry, resulting in these conformal blocks, which were found in a series of papers by Doland and Osborne. And they're of the general form of a hypergeometric times a hypergeometric, or maybe, depending on the number of dimensions, a finite number of terms of that form.
I'm sorry, Joe.
Yes?
You have a single low-dimension operator.
Right.
So why don't you have just a single operator product coefficient?
Good. Because I have a single trace operator. So what appears here? So there's also so if I have O0 of dimension delta naught, then I have then I have O0 squared of dimension 2 delta naught plus order 1 over n squared. These, because the double trace operators are protected in the 1 over n expansion. And in fact, the full set of double trace operators is just obtained by derivatives of these. and I can just take the dyadic derivative, the difference of derivatives, because total derivatives have been summed already. Okay, so the most general primary operator is just, primary double trace operator is just two factors of the single trace operator with any number of dyadic derivatives acting between them, and I can separate them into a trace part and a traceless part. So this is spin L, and L has to be even because of Bose symmetry, and so that's what's being summed in this sum, this complete set of double trace intermediate states. You'll notice there's no single trace term. We're assuming, to make things really simple. Every time we can make things simpler, we will. We're assuming a Z2 symmetry, O to minus O, so the single trace term doesn't appear. And again, relaxing these assumptions is, will be done step by step.
But it looks to be like a built-in translational invariance.
Translational. Yes, so good. So I'm assuming the symmetry even though I don't have the local operator. So this is a conformal gerb.
But actually, given this level, they can refine an operator that will generate this by its correlation.
I don't believe that you could. Well, you don't have any lever to do it with. You can define the Hamiltonian. You can define. There's a difference in having the Hamiltonian, the global generator, and the local generator. Without a Lagrangian, you really can't, I think, get the local thing. Maybe you could. Well, it won't appear in the.
I certainly could define one.
Mm-hmm.
Whether it's not you're right that the 2-point function of the intermittent in itself wouldn't be. But I could define the operator of action, and that's correlation function of these things.
No, I think not. I think that.
May not be unique.
Well, I don't know. No, if I give you the correlators, you can do something axiomatic and define. Well, you can find a Hamiltonian. I don't know if you can define the. Anyway, this is. I don't think this is something to fret too much about. This is just, convenient. Here, yeah. I'll just put lots of Muse and news everywhere, and yeah. This obvious. No, it's not obvious. It's not obvious. I agree. Of course, it's not obvious, or we would have done it.
It's all scalar. Having understood scalar.
Yeah, but I'll tell you. Yeah. Okay. So we also to the order we're working. We won't need the triple and higher trace operators either. So this is the whole thing. And so having listed the operators and mentioned the 1/n exponential, so what we have is that these operators have.
So what does that mean to the order you're working? You need triple and higher trace operators. What's the expansion parameter?
1/n squared.
1/n squared.
Since this theory automatically necessarily comes with a 1/n expansion, we're going to just solve. We're going to do as little work as possible, and so we're not going to solve it completely, but only to the leading order 1/n squared. Yeah, and also these C coefficients. Okay, and finally, the last piece of information we have is crossing. It's the same thing with Z and Z, with Z replaced by 1 minus Z and Z bar replaced by 1 minus Z bar. So I'll just, rather than copy it over again. Okay. So this is all the information that we have. We have these unknowns, and solving iteratively in 1/n, it means we have the corrections to the anomalous dimension and the operator product coefficients. We have these unknowns, and we have these equations, and now we want to solve them. And yes?
Sorry.
Yes?
I'm confused. So the bulk theory here is a single, say, large N matrix
Yes.
field. So that certainly defines some boundary correlators, which are conformally invariant.
Mm-hmm.
But it doesn't define a full conformal field here.
Because? What's missing? I mean, besides team which I don't want to hear but again.
Well, I just thought that something would. I thought that not all of the properties of the 4-point function will be there.
There's not conformal invariance. OPE is really just summing over a complete set of states.
Well, I thought that crossing symmetry was related to channel duality in the bulk, and you really need.
No, in this context, it's simply the fact that you can cut up a Euclidean path integral in different planes to exhibit a sum over states. That's all it is.
Do we want to assume the entirety, or you don't care?
Well, now so positivity. I should mention positivity would be a nice thing to assume, but since we're studying the first correction and not the zeroth order thing, which is trivial, we already know it, the first correction by itself doesn't satisfy positivity properties, so it doesn't seem as though that's a useful tool to us. I should mention, by the way, we were inspired somewhat by a paper by Rattazzi et al., who were able to use splitting crossing relations to obtain rigorous bounds on the anomalous dimensions, lower bounds. It was a very pretty paper, especially because they started with phenomenology and ended with rigor. There's not many papers that can do that in a really useful and original way. So that was inspiring, but because in particular they use positivity a lot, we're applying these tools in a somewhat different way. Okay, so here's the equations we want to solve. I don't think they're familiar in any form, although, or at least we want to show that these equations imply this locality property. I'll just mention that one thing one can do, let's count them, just figure out whether they have a chance to have solutions. We can fold into a complete set of states on Z and Z bar, or on actually Z and 1 minus Z bar, and recast these as the following. C n comma L, G n comma L A B equals the sum from n equals 0 to infinity. Actually, this is I'm leaving out an extra step here because you don't want to see them all. Okay, so this is part of the equations, just the ones that just a closed set that involve only the shift of the anomalous dimension. And again, the main point is that one can turn functions of z into things that have discrete indices via by contracting with a complete set.
Delta naught and C naught, you're just assuming it's satisfied.
Delta naught and C naught are arbitrary parameters, and the C naughts are known from free field theory. They're just the decomposition of the disconnected 4-point function in terms of double trait states, which is still an impressive bit of calculation, but it's known. So the first unknowns, the things that have the scattering in them, are these.
And the C1's strong. Is it supposed to be obvious why the C1's strong?
C1s? No. Sorry, it's not. And there's other equations. So I just doing the minimum writing, right? So there's a matrix of equations of this type involving the C's and the gammas. I just want to show them to you and hope that somebody would say, yes, I know how to solve them. You just need the following book about gerbs. Anyway.
Sorry. Even though you're on this plane, the GNL know that you're, the conformal blocks know that you're in 4 dimensions. The
conformal blocks know that you're in 4 dimensions. Actually, so they're known in 2, 4, and 6 due to Dolan and Osborne. They just get progressively a little bit more messy. In fact, again, we're working in 2, but only using the smaller conformal algebra as, again, the first warm-up. But yeah.
Isn't that then the same as the BPZ? I mean, the bootstrap.
Yeah. So right. So it's an old idea that you could solve the axioms of conformal field theory and find all conformal field theories. In practice, this has been done when one has additional information, as in the case of the minimal models or the rational conformal field theories, where there's only a finite number of primaries. And so here, too, we have only a finite number of primaries for a different reason. But in fact, it's why you think that these things might have some leverage, and they do. And so anyway, the unknowns are basically labeled by 2 integers with infinite ranges, and the equations are labeled by 2 integers with infinite ranges. And so we have enough constraints to either have no solutions or an infinite number of solutions, but it's in an interesting range. And as we add, by the way, one generalization which we haven't fully done yet, but I think is not so hard, is to have many flavors of scalar, and then everything just expands proportionately. And again, for T mu nu, it will be the same kind of relations, and so whether there are solutions, again, depends on details. So we actually know, without doing any work, of an infinite number of solutions to these equations. Namely, if we had started from the bulk with a lambda 5/4 interaction and used that will generate boundary correlators which satisfy all of the axioms that we've used. And so it's necessarily a solution to this, as one can show if one's name is Joao. And it's true. Okay, so that's necessary. And it's also local, of course. I mean, so here's a practical definition of local, that it's derived instead of this. So a practical definition of local is that it is obtained from a local Lagrangian in the bulk. And in fact, as shown by, again, Gary Giddings and Penedones, these correlators do have also the precise locality criterion, the abstract locality criterion that I mentioned earlier. But of course, there's also things like partial mu phi, partial mu phi, partial nu phi, partial nu phi. The thing with 2 derivatives actually vanishes on shell. This is the first correction. But clearly, any local operator or any finite sum of any local interaction or any finite sum of local interactions will solve the constraints. And so there's a lot of solutions. And so the real question is, are these the only solutions? So the practical definition of locality that I'm using is that the amplitudes are obtained to leading order in the 1/n extension from a local Lagrangian in the bulk. And so we're in an interesting situation. Either we find that these are all the solutions and the conjecture survives, or there are solutions which are not of this form, and they somehow represent a local theory which still has all the properties that we listed, a non-local theory which still has all the properties that we listed and therefore might be interesting in its own right. Now, we don't know how to solve these in general, but we know how to count solutions. So now we can't count yet because we have an infinite number of solutions, but obviously one thing that we can do is we can restrict to a finite number of these known solutions by restricting the growth with energy of the amplitudes, which corresponds in this language to restricting the growth with n of the gamma sub n's and the c sub n's. In fact, we're doing something which is not exactly the same, but which also restricts the interactions to a finite number in the same way, which is the following. The 5/4 interaction, if you imagine cutting it in half, since there's no derivatives, always creates and destroys pairs of spin 0. This interaction creates and destroys interactions of spin at most 2, and so on. And so rather than restrict the growth with n, we look for solutions with only a finite range of L's perturbed. Now, again, this is less physical than the restriction on the growth with energy. It's coming from the same place. And so now, for L equals 0, we have just lambda 5/4. For L equals 2 in the bulk, there were 3 solutions. Of course, now if you look at this, there are actually many more seemingly equations than unknowns, because we have a doubly infinite equations and singly infinite unknowns. And it's true that when you write these out, the first few equations determine the gammas, and the rest had better determine them the same way, or else you don't have a solution. And of course, there are solutions for the reason that I just told you. It's not obvious why, from the point of view of this abstract equation, that redundancy should hold, but it does. Okay, so I can tell you the result now, which is that the conjecture survives. We've only gone to L equals 0 and L equals 2 so far, and found indeed that at L equals 0 there's only one solution. At L equals 2 there are 3, and you know we don't have a general approach. The existence of any solutions at all, since we have more solutions than unknowns, depends, for now at least, on knowing these what are basically overlap integrals of hypergeometric functions. And they're not especially intuitive. You need the detailed form of the conformal blocks. So it would be nice to have somehow a more powerful way of looking at this rather than this brute force method. But this brute force method has carried us pretty far already. So okay, we have many things to now we see that the approach the conjecture has a good chance of being true. We have an approach that we can gradually relax the special assumptions that we've made to get to more general theories. The biggest assumption, the most troubling, of course, is that we have no energy momentum tensor. And in fact, Jan de Boer mentioned that he had thought about doing a similar exercise, and so he asked Dolan and Osborne, the suppliers of the conformal blocks, how long it would take to find the conformal blocks for spin 2, and he was told about 2 years. I don't know why it's so hard, but I have to believe that there's a way to look at this problem that will, either by abstracting out properties rather than the full conformal blocks, or by being more demanding of Dolan and Osborne, that we can accelerate this time scale. Anyway, so there we are, and if I had to bet at this point, I would bet that the conjecture is true, and I hope we can show that. So thank you.
Can't you make your life easier by working in a low enough dimension that gravitons aren't scaling anyway? So then you need a scalar, that's the leading thing.
Well, actually, that's a brilliant idea. So you say, why don't we just go to d equals 2? In d equals 3, we're basically done.
Yeah.
Good point.
But are you done if you don't take that big L to infinity? That was my second question.
So okay, right. So we would like not merely to take L finite and then L to infinity, but consider that there might be solutions with all L's non-zero, and then we have to work harder because we have to worry about the growth with L, and we have to do but yeah, that's really the next step. The next step is to relax that. Once we relax that, I imposed that Z2 symmetry, which actually left off the trilinear graphs, which you do have for gravity. So there's a series of steps to get to the real problem, but yeah, that's a great observation. Good, please.
So, but in 2 dimensions, and with just one scalar, isn't it just the BPZ with a single minimal?
Right. Okay. Good. Yes, you're right. Yeah, 2 plus 1. So even in 2 plus 1, we've only used the amount of information here in the small SO21 algebra. So if we really were interested in the 1 plus 1 dimensional problem, and we impose the information in the full conformal algebra, then yes, it would be much more constrained and reduce, as you say, to something already done. Right.
In 3 dimensions, you could. Where do you say?
Yeah, I mean bulk 2 plus 1, boundary 2 dimensions.
Okay.
So I'm pretty sure that the theory of a scalar in 2 plus 1 bulk dimensions doesn't define a boundary CFT. It might have leading order in 1 over n. But I think that one of the properties of maybe it's just modular invariance, which you're not using.
Right. So there's no guarantee working at this level either that these theories can be embedded in a full CFT with modular invariance, that is the full, or that this leading order solution in 1 over n squared can be extended to a full solution in 1 over n. So yeah, we can only say that working to this order, any solution should be expandable to this order, and to this order, it can only be of the known. It can only be of the known forms that follow from a local interaction.
Right, but so if I think of this bulk theory as coming from some element of string theory or something, at some order you're going to have graviton exchange, which is going to be important, related to the stress tensor.
Absolutely.
Isn't that there at this order 1 over n squared?
Well,
or is that,
it's not by hand here. That is, I consider a field theory in the bulk that doesn't have gravity, and it's dual to one of these gerbs, conformal gerbs. It's not just that I like when I make a joke, make it over and over again, but it's a really handy term. Anyway, but yeah, I mean, just if. I don't know if it'll be 2 years or 2 months or 2 weeks, but at some point we'll be able to give this seminar with the gravitons.
With the L equal to 2, you mentioned 3 solutions. I mean, is it like phi cubed interaction in the bulk?
No, so we imposed a Z2 symmetry that eliminates the phi cube.
Oh, okay.
And the reason is really just because, again, it turns out that in the cross channel you have all partial waves, and so yeah.
So, but then the 3 solutions, is there an obvious bulk way to?
The third one, actually, this puzzled us for a while. We thought we found something new. And the third one looks like it's spin-free because it has 2 more derivatives. But by Bose symmetry, there can't be any spin-free, so its highest spin is spin-2. Right. We don't, I mean, so what we need to sort of complete at least this piece of the approach is to have an efficient way both to count interactions and to count solutions. And that's, we have, yeah.
Can you challenge us in a different way by writing down some non-local effective action on the gravity side and seeing that it fails?
Good. This is a really, really good question. So let me give you an example of a failure mode. Suppose I had a non-local interaction which was secretly due to the exchange of some massive field. Then what you would see is that the operator product expansion breaks down because we didn't include this. That is, so there'll be a singularity as these 2 operators approach each other, so it'd be failure of the OP. Now, what we're not so clear on is what happens if we do a Gaussian smearing, where there's no singularity in momentum space. Now, so if we do a Gaussian smearing in Euclidean space, that of course rotates to something awful in Lorentzian space. And so in some sense, this theory doesn't have a Lorentzian continuation. I think the magic words are that it's not reflection positive. And so that's one way to probe the question, to ask how in fact things fail if you, good. Thank you.